Hello everybody. It is 28 July 2023 and here's the second video as promised on the empirical forecasting. Now this empirical forecasting, as said already in the first video, is used quite a lot in climate change, and that is why it is part of our research, because this empirical forecasting used in climate change, the climate change research, is also what is causing quite a lot of problems or mistakes in the climate research, and it leads to wrong conclusions. Now this once again, this also the first part and also the second part is based on this publication of ours, me, that's Peter Stallinga, and my colleague Igor Chmielinski. The paper is called Perils and Pitfalls of Empirical Forecasting, and it is from the European Scientific Journal of 2017. You can find it in stallinga.org, or at least a link to it. It is open access, so you can easily get access to this. I will also put a link to it below here, and all these things you can find on my personal site, stallinga.org. Once again, a short summary of the first video. Empirical forecasting is that you use past information in a probabilistic analysis, and to make predictions about the future. And purely empirical is that you used only past information about the predictions of the future. And as shown in the first video, that completely messes it up. It's basically it's nonsense if you don't also at least use some physics models in there. Now, and then it's two things. First of all, it cannot be done. You can only predict the past, which we call retrodiction, or hindsight bias, or something like this. And actually then also the idea that the second problem is that you assume that nature is probabilistic. It's called the Ludic fallacy, as Mr. Nasib Taleb calls it, that as if nature is constantly throwing dice. And this is not necessarily the case. And then the third problem is that the function that is then normally used in modeling the probabilities is normally this Gauss curve or the bell curve or the normal distribution, and also that is quite dubious, to say the least. So in the second part we are talking a little bit more. I'm going to talk here a little bit more about these functions. So this function we're talking about is the bell curve, which is probably here to see the probability distribution. It looks like a bell for some kind of parameter x, and then the probability density x. It is based on, basically it is very well modeled on basis of the idea that throwing or flipping a coin is a probabilistic event, which it isn't, because it's nature and it depends on the laws of nature, of gravity and friction and things like this. So it's not probabilistic at all, but for us it looks probabilistic because we don't understand the physics behind it, or we don't understand the starting conditions and so on, or we don't have enough computation power to calculate what's going on. But the outcome of flipping a lot of coins is sort of like this bell curve. Or in the function, as you can see here, it is exponentially, quadratically exponential. So it's very often used for climate data. For instance, you see here the climate events, the temperature measured virtually, a virtual measurement in the country of Gulliver's Travels. And similar to the frequently asked questions 9.1 of the IPCC report of 2007, and then suddenly they measured an outlier and they see this as climate change, because in this model the average of these measurements, that is the climate. The 30-year average of that's the climate. This one you model with what is the parameter mu, that is here, the parameter mu, and then the weather, the spreading of this weather, the events around this average, that we can call then the weather variability, and that is then modeled with sigma, that is the width of this distribution curve. Okay, remember this, so far so good. It's mu is the climate and sigma is the weather, we could call it, just to remember this. So if they get to this outlier, they say that climate has changed. But immediately you can say that that cannot be the case, because no bell curve will fit, no mu and sigma parameters, it has only two parameters, will actually produce this kind of value. Even if we adjust this bell curve or change mu, it will not then predict with any probability, then it will produce this value. So it would immediately be wrong anyway. So what they're doing, we're forcing that the data in some kind of distribution, Gaussian, we do here, and then when a data is not conforming, instead of throwing away the idea that the function that we choose was wrong, or that it is actually not probabilistic at all, we're just saying that the climate has changed, that it's an outlier, and therefore we have to change the climate parameters. Nobody will say that the assumption of the Gaussian probability distribution is wrong in the first place. So that is a severe problem. Now, we arrive here to the second part. Let's see, where am I now? This is with the die roll. I think we have to go here to the break. We're talking here about we're talking about distribution functions, and I will talk about extrapolations also in this second video, and about correlations between data, because they seem to be sort of like related to the climate subject. So first of all, they use, for these probabilistic functions, they very often use this Gauss curves, or Gauss-like curves, or which is called the bell curve or the normal distribution. And we have to say in advance, there is no logical base for requiring probabilistic functions at all. Nature is not necessarily probabilistic. And even if it is probabilistic, it's not necessarily the Gauss curves. And the problem with this is that people use this a lot, because this is very easy to deal with. It reminds me of this joke. There is a man in the street under a street lamp, and he's looking for something. And the other guy comes to him and says, like, "What are you doing?" He said, "Oh, I'm looking for my keys." "So where did you lose them?" "Oh, there, around the corner." "Oh, so why don't you look there?" "Oh, because there it's dark and here it's light." So you see, people use the Gauss curve because they are light. They know how to use it. They know how to deal with it, and they don't know how to use dark curves, which actually we will see is they cannot be used in probabilistic functions. But it could well be that this is what nature is. We're not the only ones that make this remark. Also notice here, for instance, Wendler and Muzaffar. They write, "Our purpose is to criticize the belief that the normal curve distribution is a representation of real things in nature." There you go. And also read somewhere, I cannot find it back where I read it, that the experimental people, they think that it has a base in theory, and the theoretical people, they think that it's been proven by experiment. And neither is the case. People just use it because this is the only thing that they know how to use. And if you have a hammer as a tool, you see all problems as a nail. So here we have the problem, for instance, where does this function of the bell curve fit quite well? This would be like things that are, let's say, limited in possibilities. Let's say coin flips, which you have only 2 probabilities. So the amount of probabilities when you throw n coins, this is then also, it's limited. And when you throw a die, the die roll, then the next die roll will have an average, a probability function. So that you understand then that there it works quite well. With this kind of systems, it seems to be working quite well. And even if it doesn't make sense, because nature, even throwing a die, is not probabilistic. It is actually fully deterministic in nature. But for us, because we are not knowledgeable about the system, we don't have enough calculation power or something like this, we can do as if it is probabilistic, but it isn't. But for a die roll, you could, in this way, if you really want, you can make a probabilistic analysis and then say that you can predict on basis, not actually on basis of the past data, which goes wrong, watch the first video, but you could, on basis of a physical model, that you know that the die has 6 faces, which are, it's a symmetric object, and therefore all 6 faces would have an equal probability in your non-probabilistic, or in other words, deterministic, you could say, model. But there's other systems that are not so limited like this, and this can completely mess up the entire analysis. It is not possible to say anything about the expectation value of the next earthquake in San Francisco, because that's not a limited system. The amount of possibilities is not limited. And these do not follow probability statistics. So also bell curves and things like this, they are nonsense. But for the climate, what do? They say assume the events are normally distributed and that it is of course probabilistic. Find the parameters mu and sigma. Mu is the climate, sigma is the weather, remember, and then determine by a student's test if a new data point lies within 2 sigma or not, within a distance from the center, from the average, from the mu. If not, if it is further away, then we say that the parameters of the distribution have changed and therefore we have climate change. The reasoning goes wrong with the basic assumption, namely of the distribution being Gaussian. Upon arrival of a new data point that is falling outside the expected range of the normal distribution, it is then concluded that the parameter mu has changed, climate change. But instead the conclusion should be that the data are not distributed normally, or actually that there is no distribution at all. So the only thing is, if there is no distribution that is normally, then the only thing that we are remaining with is a frequency of occurrence, or a tallying statistics. So nothing to do with probabilities, only probabilities of the past, which are frequencies. And this you can also call binning if you want, but then you are this kind of things you could do. You could do frequency analysis of the past data. And then there are basically 2 types of functions like this. This is also based on the work of Nassim Taleb. But I put it here a little bit more in a mathematical format, which he doesn't, unfortunately. But there are basically 2 types of functions to describe the tail behavior, because there is where the problem is. The tail behavior, the data points that are far away from the center, behavior statistics in nature, frequency analysis, frequency of occurrence analysis in nature, namely exponentially, like the Gaussian bell curves. But they are called non-scalable. We will see in a moment why. And there is also called the ones that are called they are power law. They are called Pareto functions or Zipf law or things like this, and they are scalable. They're scalable. They're scalable. I have to be very careful what I'm saying. And actually, what also Mr. Taleb says, we use the bell curve because we know how to use them. It's easy to use them. We are fooled by the reductionist need of simple functions. But there are functions that are actually more adequate for nature, and they are scalable, and they are not easily to deal with for the reason that I will show in a moment. Just to show you that this what Mr. Taleb actually mentions, scalable functions, that is defined here as that if you go from x to ax, introduces a constant factor in the function value independent of x. For instance, an earthquake of Richter magnitude x has 8 times more occurrence than an earthquake of magnitude x plus 1, independent of x. So an earthquake of magnitude 6 has 10 times, for instance, imagine like this, has 10 times less probability than one of 5, and one of 7 has again 10 times less probability than one of magnitude 6. And then in this publication, the British Journal on Mathematics something, actually I forgot, I apologize, from 2016, I proved that this definition of Mr. Taleb, that actually the only functions that follow this is the power law as shown here. So these scalable functions, they are power law functions, and they have a huge problem. They are horrendously difficult to work with, as I also have done in my electronics analysis work. If you have power laws, you're basically in deep shit, because they are like this. They cannot be worked with. You cannot do anything with this. And the reason with that is that they have a fat tail. There are some once in a while occurring high magnitude outliers, black swans, that mess up the entire analysis. Or to put it in another way, let's assume here that you want to calculate something with it, And if it's a probability function, then the idea is that a probability function must integrate to unity. And if it integrates to unity, then it's okay. Then it can be assigned probability. But the power law function can never integrate to infinity. If you integrate it from 0 to infinity, like this, if you take all the parameters, all the possibilities, this function will always result in infinity, independent of the value here of alpha. It always winds up to infinity, either on the 0 side or on the infinite side of things. So they are not probability functions. And if they're not probability functions, then they can obviously not be used in a probability analysis like empirical forecasting. So then it's basically a game over. So very often what they're doing is they use truncated power laws or something like this, or delayed power laws or whatever, anything to avoid the impossibility of having infinity in the integral. Here I show why they are called scalable, because here you see this power law things, this dashed line, they're called scalable, and the bell curve is called non-scalable. This is called scalable because if you zoom into this scalable function, you will see the exact same function. You can then also, you could call it a fractal function, because zooming in you will result in exactly the same structure of the function. That's why it's called scalable. And to make it even worse and make it more confusing, that's why I'm also always confused myself, a scalable function has no scale. So you cannot say, for instance, that's also in electronics, is what time does it take for a transistor to degrade? You cannot say, because it doesn't have a time scale. For a bell curve, you could say this. You could find a parameter, which is this width, the sigma, as you know. That is the scale parameter of the curve. Scalable functions are they have no scale, while non-scalable functions, they have a scale. Yet, if we scientists model the system with bell curves and find data that are not consistent with it, we prefer to throw away the data. We call it outliers, or we say that there's been the parameters have changed, that it's called climate change. But what we should do is say that the data do not follow such nice, beautiful, easy to work, non-scalable functions. So this is what we always call, funnily in science, we say, trust your model, facts can be disposed of. Just keep to your scale, to your bell curve, because the bell curve you know how to use, and the other ones you do not know how to use. So in general, we could say, summarize this about the functions that scientists, in an attempt to describe nature, use stochastic models which necessitate the use of probability like docile functions, i.e. Gaussian bell curves. If in this way we manage to successfully describe 99% of the real situations, we are happy. The remaining 1% are just outliers. We sweep them under the carpet and they don't discourage us. The 99% success rate validates the stochastic model approach. Well, as Mr. Taleb in his book says, The Black Swan, that one day there will be one of these outliers which will actually completely destroy your entire analysis and will make you go bankrupt or something like this. He specifically talks about the economy or risk management for investors. They will do risk management based on the bell curve, and then there will be one day there will be going something so wrong that they will all go bankrupt. Okay, so much for these functions that were used in empirical forecasting. Empirical forecasting by itself is already nonsense, so to say, and using the bell curve is very dubious in very many cases. Now let's start another subject about extrapolation. So imagine we will continue with the bell curve, and maybe this bell curve is even actually correct. And actually the climate, let's talk about climate, the climate parameter mu, which was the average of the past data, the past 30 years data, they can actually be a function of time. They can change over time. And so climate change, let's say we call it here a linear climate change. The climate is changing, the temperature is changing linearly. So we have it here a linear function that the average prediction value the average prediction value of for future data actually now depends also on time. So we get a linear rise. As we all know, extrapolation is not allowed on the basis of the data alone. If we don't have a model to say why it should be linear increasing, then we should not use extrapolation at all. We can only do interpolation, so that is between the data points and not beyond the data points. And this is already, we know already from our mathematics and physics lectures that this is not allowed, unless we understand the physics behind the system and have explained that it should be linear. If not, actually, then we should use a simpler model that we should make it constant. And then is also here given by another great book of another great scientist, which is Mr. Daniel Kahneman in his book Thinking Fast and Slow. He explains it in his chapter on regression to the mean or regression to the average. Imagine a golf tournament. A player's score is determined in part by his skills, but also a great extent by his luck. So that is the spread of the distribution. And his skills would be like the mu, and his luck would be the sigma. Thus, if after one day a certain player is on the first place of the leaderboard, it is because he is skilled and had exceptional luck. While his skills wouldn't have dwindled much overnight, his luck is expected to be average next day. And thus we expect him to drop on the leaderboard. This is counterintuitive, and most people will expect a person leading a tournament to continue to play well and continue leading, in fact extend his lead. That is because people use an empirical analysis extrapolating past performance for a prediction of the future. So then you do extrapolation of something that cannot be extrapolated. It has exactly the same problem as empirical forecasting. And now you do empirical forecasting based on the data, on making a linear analysis, a linear extrapolation in time. And this is not allowed for the exact same reasons as the static analysis of past data is not allowed. Also the linear changing data of the past is not allowed. Reality shows us this, that regression to the average is to be expected, and Mr. Kahneman has shown this in very nice detail, very many experiments. He shows that basically he talks about investors and so on, that normally the performance of these people is going back to the average, meaning you had a constant. Even if you have climate that seems to be changing, the prediction for tomorrow is to go back to average climate. The same type of reasoning may thus be applied to the climate. In 1998 we had an exceptionally warm year. This was due to climate change, equivalence of skills to the player, but also due to random variations like the luck of the golf player. The conclusion of the people using an empirical approach only was that it would warm up even more. Yet regression to the average told us that after an exceptionally warm year it was bound to cool down, as indeed happened. After that we will get what is called the pause, and then this pause had to be removed by data tampering techniques, as we all know. Apparently a staggering failure. We have regressed to the mean of linear warming up. We are actually now the linear warming up that we have seen, that is actually still taking place, and there's nothing exceptionally going on. Climate scientists starting here now a different subject, that also now imagine that we have this. This would be the melting of ice on Greenland. So it's melting, and every 50 years we will get a huge deposit of new ice on in Greenland. Now, if you measure only part of it, you constantly see melting. You always see melting. Whatever 2 years you would actually do on this slope here, you see melting, and you would extrapolate and say that it's melting. But once in 50 years you get an event that deposits a lot of ice. So you see that on the long run there is no melting, but when you do a simple linear extrapolation you would expect that the ice would be gone, like Mr. Al Gore said. The polar ice would be gone in 5 years, he said in 2009. So in 2014 all the ice should be gone on the North Pole, and it isn't, because we got regression to the mean, or we got, let's say again, an event that deposited a lot of ice. So this is about Greenland, but it can also be about the North Pole or anything like this. So it can also be about the temperature, regression to the mean. As long as you don't have a model, that would explain it, then you cannot do this analysis. You have to have a model. Just doing this kind of experiments, this kind of predictions based on the data alone, there it goes wrong for static analysis and also for extrapolation. Okay, so now let's talk about the third subject here in this video. It is about the correlations. And in correlations you can also make very big mistakes. And this is relevant to the climate because you all know that the temperature seems to be correlated to the carbon dioxide in the atmosphere, and then they have retroactively invented the idea of that it would be caused by the greenhouse effect. But look at this. In medicine, a correlation exists between high cholesterol levels and cardiovascular problems. Pharmaceutical industry has used this correlation to sell its idea that their cholesterol-lowering medicine, statins, would be beneficial for the public. Well, and then they started selling this, and there is no huge effects of this selling the statins on the cardiovascular problems. And that is because they forgot, like always, also an alternative explanation might exist, namely that high cholesterol levels are caused by a risk of cardiovascular disease and the body fighting the risk by increasing cholesterol levels. So it's the cholesterol that is fighting your cardiovascular disease. So it might even be the exact opposite. So now if you start lowering the cholesterol levels, you're actually killing people. I'm not saying that it is like this. I'm saying that it is possible, and they never thought about explaining the correlation in this way. So that is then a big problem, that the correlation, even if they're correlation and if they are cause and effect linked, you don't know which one is causing and which one is the effect. In the same way, in the climate, a high correlation was found between atmospheric carbon dioxide concentrations and global temperature. This correlation was only seen in the past, while recent huge amounts of CO2 injected to the atmosphere apparently were accompanied by a lowering of global temperature since 1998. So even the correlation is absent or not so big in modern and contemporary data. So we start thinking maybe the correlation is the other way around, that carbon dioxide is not causing the temperature, but is the result of temperature. And this is well possible. So the biggest problem with correlations is you don't know which is causing and which is effect. So let me put this in a figure. I have here 6 possible reasons why data are correlated. It can be completely coincidental, like a coincidence. They're just by possibility. They just coincidentally they are correlated, and what they want us to believe is that A is causing B. But as I explained to you, it might as well be that B is causing A. But anyway, this we call unidirectional causation, correlation, that one is causing the other. But there are 4 more correlations possible. So that is also that both A and B have a common base, X, normally called a confounder. Okay, it can be transitive. A is causing X and X is causing B, but A is not causing B, and I will give examples in a moment. And also it can be combinative, that A and X together are causing B, but A or X independently not causing B. I invented here an example like water plus cold gives ice. If you have only water, you don't get ice, and it's only cold, you don't get ice. This unidirectional talked about. Bidirectional is A causing B, but B is also causing A, and this is the most interesting from an engineering point of view, because that is feedback theory, and I actually also already talked in other videos about this feedback. Now, one indication is if A is causing B or B is causing A. Notice that in the atmosphere, in the climate, it was shown that carbon dioxide is lagging behind temperature variations by some thousands of years. Indermühle found 900 years actually for the delay. And then you have basically it's game over for the idea that A is causing B, because then B must be lagging behind A. And it cannot be that B is ahead of A if B is the result of A. So it cannot be that carbon dioxide is lagging behind the temperature if carbon dioxide is the cause of temperature. I guess that must be very clear. And as I already told you, they can have a common base. The cholesterol problem or the cardiovascular diseases problem, they can have that both of them can have a common cause in our DNA. Something in our DNA causes us to have a lot of cholesterol and causes us to a lot of cardiovascular problems. So this is DNA, cholesterol, and cardiovascular problems. It's obvious that if you change your cholesterol level, it will not change anything with your cardiovascular problems. And look at this one. This one is funny. In the 1950s, doctors balanced the fight of the body with infections in favor of the bacteria, based on irrefutable correlations between low iron levels and infections. So doctors were giving iron supplement to sick patients, thereby factually killing them. Note that bacteria need iron much more than our body does. So our body, to fight against infections, is actually removing iron from its body so that the bacteria die. Our body secretes iron in order to kill the bacteria. Now this is then also funny that the myth of the benefits of iron was further amplified by the comical character Popeye eating spinach, thus combining two myths in one, since apart from iron having no benefit on an infected person, also spinach does not contain so much iron as previously claimed. So you see that how sometimes very funny myths can go into society, and actually some of these myths, they can actually kill people because they were giving iron supplements to feed the bacteria in infected people. In this one also, number 3, this is transitive. A is causing X is causing B, but A is not causing B. And let me give you an example. This is one I invented myself. Imagine politicians listening to scientists that analyze health of people. We know that men, imagine this, that men are smoking more than women, but we also know that smoking is bad for our health. So A is causing B, A is being a man, is causing that you're smoking, and smoking is causing cancer. Lung cancer, for instance. So now the correlation is that being a man is bad for your health. And the obvious conclusions of the scientists will be that being a man is bad for a person's health. And politicians will implement mass splenectomy measures on basis of these scientific facts. If you don't understand what's going on, then you only use correlations, which is only using correlations is as stupid as using this entire idea of retrodiction, of empirical forecasting, and of linear extrapolations or extrapolations in general. This all comes from the same scientists' fool's tools, I would call them, that you can be fooled by them by thinking that correlations is actually something meaningful. The conclusion is that if we use an empirical approach, analyzing the data without a good theory to explain them, correlations can and will fool the scientists, so you should be very careful. Now, to sum up this entire 2 videos, these are these points that I would like to pass on to you. That first of all, if we use a purely empirical data-only analysis, we can do this only of the past data, and any predictions for the future are meaningless. And point number 2, we have to know what the probability function is, if the system is covered by probability function at all. Number 3, in case the distribution function is not probabilistic, like the power law observed for many phenomena, no prediction of the future can be made whatsoever. Just mathematically it's not possible. Likewise, if we want to make extrapolations based on trends, we are only allowed to do this if we have a good basis for our extrapolation function. So we need physics models and not only the data itself. And here an example, after an extreme event, an outlier, it is often said this event was extremely improbable and is thus a sign of climate change. The word thus is imagined by the public at large, because no scientist will ever utter this. Weather and climate do not follow probability distribution. This is something else, sorry, this is some other comment. Weather and climate do not follow probability distributions, but only reality, frequency of occurrence distributions, and thus any probabilistic analysis is meaningless. The second part, climate change, is an empty statement, since anything that is not equal to the past average is a sign of climate change. So now about the correlations. Blind analysis of correlations does not make sense. I guess that you also agree to that. I hope so. All in all, we must conclude that the empirical approach of these 3 points, empirical forecasting, empirical extrapolation, and empirical correlations, these 3 points, that this is a simpleton's tool and a scientist's nightmare. Any analysis without an understanding of the underlying processes is full of perils and pitfalls. The approach of the scientist represents the level of understanding of the system, ranging from completely ignorant, fully empirical, everything based on past data, and then we use probabilistic functions and so on to predict the future, from completely ignorant to completely sapient, meaning that we just apply the physics laws and there is no prediction probability function because we just, like Mr. Aristotle, we just say that we know what is going to happen. Like Mr. Aristotle, this entire work is based on his words. He said that only that what will happen can happen. In other words, tomorrow the probability of rain is either 0% or 100%. Either it is going to rain tomorrow or it is not going to rain tomorrow, and there is no probability 30% rain or something like this. And if we are very sapient, we actually can calculate if tomorrow it's going to rain or not. So I hope you enjoyed these 2 videos, and maybe see you in the next video in the future.